Hi, I'm James, the Bald Engineer. Both of these are transistors. One is a BJT and the other is a Mosfet. Can you tell the difference? If not, that's okay, because in this Adams video, we're going to take a look at Mosfets, how they work, and how you can use them in your circuits. So let's get going. This video is part of a two-part series on transistors. The previous one covered bipolar junction transistors, BJTs, while this video covers metal oxide semiconductor field effect transistors, known as Mosfets. Generally, you'll use a BJT for small loads, say less than 1 amp of current, while Mosfets are well suited for applications with much higher current. For the video on BJTs, see atoms.com/EP10. For now, let's move on to Mosfets. Moss is a flowerless plant that typically grows 1 to 10 centimeters. Some mosses grow up to 50 centimeters and can be commonly found on trees. Wait a minute. This is the wrong script. Hold on. The tree sounds right. Okay, here's the other stuff. Okay, let's try this again. Mosfets belong to a family tree of field effect transistors, or known as FETs. There are JFETs, Mosfets, and IGBTs. JFETs actually work a little bit like a BJT, which we've already talked about. For this video, we're focused on the Mosfet, which has two types of modes called depletion and enhancement. A depletion mode Mosfet works like a normally closed switch. Current can flow when no voltage is applied. Applying a negative voltage actually causes the current flow to stop. An enhancement mode FET works like a variable resistor. They come in N-channel and P-channel types. Enhancement mode FETs are by far the most common transistor used today, so let's focus in on them. Here's the symbol for an N-channel enhancement mode Mosfet. And here's a TO220 style transistor. The pins of a Mosfet are identified as the gate, the drain, and the source. The field effect part of their name suggests they work by voltage, compared to a BJT, which works by current. When voltage is applied between the gate and the source, current is allowed to flow between the drain and the source. Here's the really cool thing about Mosfets. They are variable resistors controlled by voltage, which means depending on the voltage applied between the gate and source, the resistance between the drain and source will vary. With a low voltage at the gate, the resistance from the drain to source is very high. It's kind of like an open switch. As we increase the voltage at the gate, we pass a threshold voltage, and then the resistance from the drain to the source drops, and it drops very quickly. The key difference between a Mosfet and a BJT is that the output current isn't a multiplier of the input, because Mosfets are all about voltage. Since the resistance is between the drain and source, it is known as RDS on, and can always be found in the Mosfet's datasheet. For example, this is a FQP30N06L. Let's take a look at its datasheet from Fairchild. We can see that RDS is given when there are two different voltages from gate to source. At 10 volts, the on resistance will be about 27 milliohms. And while at 5 volts, the on resistance is only about 35 milliohms. That's pretty small when you think about it. We picked this Mosfet on purpose. It is known as a logic level Mosfet because the voltage from gate to source, VGS, is lower than 5 volts. In other words, the threshold to turn the Mosfet on is low enough to be used by an Arduino or Raspberry Pi. Not all Mosfets are logic level compatible, so it is very important to check to see what the VGS threshold is before using it in your circuit. Since you will probably use a Mosfet in high current applications, it is important to check how hot it is going to get. Here's how we calculate if we need a heatsink or not. The formula to determine how much power the Mosfet dissipates is resistance times current squared. In this case, the resistance is RDS on, and the current is whatever your load will draw. Let's use an example of a motor that draws 1 amp of current. This means we multiply 35 milliohms by 1 amp squared to get 35 milliwatts. Okay, now we need a few more things from the datasheet. First, we need the junction to ambient coefficient, which is R theta JA, and in this case is 62.5 degrees C per watt. We also need the maximum junction temperature, which in this case is 175 degrees C. Using this formula, we can calculate the maximum power the transistor can dissipate without using a heatsink. We take the maximum junction temperature minus the ambient temperature, which is going to be 25 degrees C, and divide by the thermal resistance. This gives a maximum dissipation of 2.4 watts. In our example, we are only dissipating 35 milliwatts, so we're safe to operate without a heatsink. Now, you might be wondering, how can the number we calculate be 2.4 watts when the datasheet clearly said 79 watts? And that's a really great point. The 79 watts is if we had the ability to cool the transistor's case to 25 degrees C, which means you have to be using some kind of heatsink. But we're going to cover more on that in a later video. Let's review what you need to know to use a MOSFET as a switch. Number 1, find out which pin is the gate, drain, and source. Number 2, look at the datasheet to determine the threshold voltage, which is going to be shown as VGS or VTH. Find the drain to source resistance or RDS on. Number 4, look at R theta JA and the maximum junction temperature to calculate how hot the MOSFET will get. Visit adohms.com/MOSFET-guide, all lowercase, to download a simple PDF form you can use to calculate these parameters. MOSFETs are cool little devices, but they're also a little bit complex, so we'll cover them in more detail in future videos. Make sure you follow us or subscribe to know when new video tutorials are released. If you visit adohms.com, you can also get show notes for this episode as well as other Adohms videos. If you have any questions about MOSFETs or ideas for future videos, send them our way and keep watching. Maybe we'll cover them in a future video.